Hello once again and welcome to Wagner Academy here. We have the Chapter 2 review for geometry. With any review that you find on here, please try the problems yourself first. The intent of this video and these review videos is to help you with the problems you don't understand and to give you further explanation. If you get a problem but not quite fully get the problem, you don't really understand why something is the way it is, you just know how to get the answer. This will help you out with that too. So let's get started. And here it says, write the statement in if-then form. Determine the hypothesis and conclusion, and write the inverse, converse, and contrapositive. So we got a lot going on in this one. I'm going to use red to start. Sure, why not? And we'll go here with number 1. So if-then form. We are dismissed early if there's a teacher's meeting. I can change that into if-then form by writing it like this. If there's a teacher's meeting, then we are dismissed early. So notice the if-then form in there. I have if, and then this part right here. What is that part called? Well, I'll just use my green here. The part after the if is called the hypothesis. So I've identified the hypothesis right there. And then the part after the then is the conclusion. So here's the conclusion. So we've got that part done. Now we're going to write the inverse, converse, and contrapositive. Ugh. I wish I could write as well on here as I do on normal paper. I usually have very good handwriting. It's not bad here. Hopefully you can read it without any trouble. But I just wish I could write just as well. I'm working on it. I'm trying to get better. So the inverse. What do we do for the inverse? We're supposed to negate both things. And so by that I mean negate the hypothesis and negate the conclusion. So this would be the inverse if there's not a teacher's meeting. And I can spell just a second. There we go. If there's not a teacher's meeting, then we are not, or aren't, you could say either way. They're both grammatically correct. We are not dismissed early. The converse. I like to think of Converse shoes, and I think of switching brands to Converse shoes, switch the hypothesis and the conclusion. A lot of people like Converse, at least when I'm taping this video or making this video. Still pretty popular to wear the, I can't think of the name of the most popular Converse shoes. You can comment on this video and tell me if you remember. So we're just going to switch the conclusion and hypothesis around in the Converse. So if we are dismissed early, then there's a teacher's meeting. And the contrapositive finally. The contrapositive, it's kind of a big word. It puts both of these things together. You do both. It's the most complicated one. It's the most complicated sounding word. I think that's a good way to remember it. It's the most complicated one to do, or it just involves the most. So we're supposed to take the two statements, switch them around, and negate them, and put knots in there. So basically, I can start with the converse and just insert knots into there. This one's already switched around, so if we are not dismissed early, then there's not a teacher's meeting. And again, I can spell, I promise. Here we go. Teacher's meeting. There we go. So that's number one. Not hard, but it just took a while because we have to write out the whole sentences. All right, so number two. I prepared dinner on Wednesday nights. Notice no if, no then to begin with in this sentence, but we can insert it in there. What would make more sense, or what would be the logical way to do this? Are you going to say if I prepare dinner, then it is Wednesday night, or if it is Wednesday night, then I prepare dinner? If you said the first way, if I prepare dinner, then it is Wednesday night, it's not necessarily true, because it could be Thursday night and you still are preparing dinner, or Friday night. But if it's a Wednesday night, according to this statement, you are preparing dinner. That's your night to prepare dinner, the way this statement is worded, the way this sentence is worded. So I could put the initial conditional statement, the if-then statement, like this. If it is Wednesday night, then I prepare dinner. That is a logically equivalent way to say this same statement, but just in an if-then form. So again, the part after the if is the hypothesis. Let's identify those parts first. And the part after the then is the conclusion. And back to the inverse, converse, contrapositive. So the inverse, we are supposed to put nots in there. We're supposed to negate them. If there's nots already in there, then we double negate. And just like a double negative equals a positive in math, it does as well in logic. But there's not nots already in here, so we're just going to insert them in there. So if it is not, or isn't, I'll go with isn't just for fun. If it isn't Wednesday night, then I do not, or don't would be a good way to say that. Then I don't prepare dinner. Now, are we saying with any of these statements that we've said so far, are we saying this is true or false? No, we're not going there. We're just making the statement itself. We're not saying that this is a true statement or a false statement. We will be getting to that as we progress in this review. The converse, we're going to switch to the hypothesis and conclusion. And we would say if I prepare dinner, then it is Wednesday night. And then finally the contrapositive, that's the most fancy or complicated sounding word, and it involves the most things to do. We are going to switch and negate. We are going to say if I don't prepare dinner, then it isn't Wednesday night. And that'll do it for 1 and 2. Now let's move on to 3 and 4. It looks like these are filling in the blank and then drawing a sketch that illustrates your answer. So let's divide this up into a couple different parts here, since I'm going to have some sketches. Sounds like a good idea. Number 3. Through any 3 non-collinear points, there exists blank plane. I wish they would have done this actually, because that kind of tips you off to what the answer should be. So non-collinear points, so these are points that do not lie on the same line. If they did lie on the same line, you could have multiple planes going through those points. But here's 3 non-collinear points. This is drawing a sketch of this situation. So that's a possible sketch of the situation. There is just one plane. That's what goes in the blank. That's how we define, or that is a postulate about points and planes. So number 4, a line contains at least blank points. So how many points do you need? Another postulate about points and lines. Here, how many lines or points do you need to make a line? You need 2. So you have to have at least 2 points to define where the line is going to be. So are there actually more points than that on any given line? Sure are. There are an infinite number of points on any given line, but you need at least 2 points to determine where that line is. Number 5 and 6, can the statement be written as a true biconditional statement? So here's number 5. A biconditional statement, when you see that prefix bi, you should think to, like a bicycle, or think both. In this case is a better way to think of it. Does it work in both directions? Does it go both ways? If x equals 5, does it have to be true? Does x equals 5 imply that x squared must equal 25? Is that true? Yes, it is. So this is true. I'll put a check mark there. That always works. If x equals 5, you square 5, you always get 25. However, if you switch that around, it has to work both directions. If you have x squared equal to 25, does that imply, does that mean, and some of you may draw your imply arrow with a single line like that too. Just kind of depends on the book and what they say. I'm accepting of either way, but just check what your teacher says and verify with them that they're okay with either one of these. But if x squared equals 25, does that necessarily mean that x has to equal 5? If you say no, you have to say what the counterexample is or what a counterexample is. There might be more than one. In this case, it is no. What's the counterexample? Counterexample would be that x equals -5. If you had x squared equal to 25, it could also mean that x equals -5. This is a counterexample to the converse of the original statement. We switched the two things around. So we found a counterexample. Can the statement be written then as a true biconditional statement? You would say no. It cannot be written as a true biconditional statement because it does not work in both directions. So because of this not being true necessarily, we say no, it's not a true biconditional statement. How about number 6? A rectangle is a square if, so here the part after the if, this is what we're going to start with, if it has 4 congruent sides. So we're saying it is referring to a rectangle. So a rectangle, I'm going to just abbreviate some things here, has 4 congruent sides. Does it work in the conditional direction, in the if-then direction? So if it has 4 congruent sides, does it have to be, does that mean the rectangle is a square? Does that have to be true? Well, if a rectangle has 4 congruent sides, let's draw a picture of that just to show that. A rectangle, remember, by definition, has 4 90-degree angles. That is needed in a square, and if it has 4 congruent sides as well, that's the definition of a square. And so if this is true, the rectangle has to be a square. That's the definition of it right there. So I would say yes right there. Now if we switch that around, is it still true? Does it still have to be true? If a rectangle is a square, so you start off with this now. Does that imply that the rectangle, it in this case, you could say as well, because you've referred to what it means. So if a rectangle is a square, does it mean that it has 4 congruent sides? Sure it does. If you start off with this, if you start off with a square, by definition it has 4 congruent sides. So that works out. Therefore, it can be written as a true biconditional statement. So I would say yes. And if you were to write it out, it doesn't ask you to do that here, but if you had to write it out, you would say a rectangle. And if I'm going to go with the initial conditional statement the way it was written, I would say if a rectangle has 4 congruent sides, then a rectangle is a square. If I start off with that thought, I'm going to put this part first. A rectangle has 4 congruent sides. I'll use some abbreviations here. If and only if it is a square. So if and only if that implies that it is a biconditional statement. We check the truth, the validity of the biconditional statement by checking both the conditional and the converse. And so if you had to write out the biconditional statement, it would look like that. Continuing on with numbers 7 through 10 here. Write the symbolic statement in words using P and Q given below. So P is this statement. P is a statement that angle A is a right angle. Q is this statement. The measure of angle A is 90 degrees. And so P implies Q, that could be the conditional. Q implies P would be those two switched around. That would be the converse of that statement. In words, though, what would that look like? It would look like this. Start off with Q. If the measure, I'm going to shorten it up like that. If the measure of angle A is 90, I feel like I might be cheating a little bit there. I'll write it all out. I would accept it as you. If I were your teacher, I would say that's okay if you wrote it shorthand like that. But I'll write it out in case your teacher's not as forgiving as I am in that case. So if the measure of angle A is 90 degrees, then angle A is a right angle. And it specifically says write the statement in words. So yeah, probably a good idea that I'm writing it all out. Okay, so not Q implies not P. What would that look like? I'm going to start off with the negation of Q. So if the measure of angle A is not or isn't 90 degrees, then angle A is not a right angle. So notice it's the same as number 7, just negated. I have nots in there. And so we have the contrapositive of, if the initial statement was P implies Q, that's the contrapositive of P implies Q. Number 9, just not P. What would that look like? You have no if-then statement. If you're just using the P statement, you just say angle A is not a right angle. It's not really a sentence, it's just a statement, but they've got a period, I'll put a period. And then number 10, not P implies not Q. That would be the inverse of P implies Q. We're going to have nots in front of the statements here. And again, notice with all 4 of these, I'm not saying this is true or false. I'm not testing the validity of the statement. I'm just writing the statements out. So I've got if angle A is not a right angle, then the measure of angle A is not 90 degrees. And now number 11 and 12, we're going to use the law of syllogism to write the statement that follows from the pair of true statements. So they are saying that these are true statements here. This statement, both true statements. They're just saying we're assuming that's true. This statement, assuming those are true as well. The law of syllogism basically comes down to this. If you have a first thing implies a second thing is true, and the second thing implies the third thing is true, then you can just say the first thing, you can go right from the first thing to the last thing. You can say 1 implies 3. So that's a law of syllogism in a nutshell right there. So let's apply that to these two problems. Number 11, writing the statement that follows. So if there is a nice breeze, that would be like statement 1. Then the mast is up. That would be like statement 2. So there's a nice breeze. The mast is up. That's statement 2. The mast is up is statement 2. Then we will sail to Dunkirk, or Dunkirk would be statement 3. So we can start with statement 1. If there is a nice breeze, then we can go right to statement 3, not C, statement 3, and say then we will sail to Dunkirk. Where is Dunkirk? I don't know, but it sounds like a cool place. All right. How about this next one? Chess Club meets today. That would be statement 1. Then it is Thursday, statement 2. It is Thursday. There's statement 2 again. Then the garbage needs to be taken out. Statement 3. So we can go right from 1 to 3 once again here. So we can say this. If Chess Club meets today, then go right to statement 3. The garbage needs to be taken out. Now let's check out some matching problems here, it looks like. So match the statement with the property. We've got 13 through 16, A through D. If if the measure of angle S equals 45, then the measure of angle S plus 45 equal 90. What is that an example of? If you add 45 to 45, you're saying S equals 45, you could replace 45 right here with the measure of angle S, or you could replace the measure of angle S with the 45 that you see there. And so it looks like, though, that we're adding 45 to both sides. We started with this equation right here, measure of angle S equals 45. If you add 45 to both sides, you would get this statement right here. Adding the same thing to both sides, that right there is the multiplication property of equality. So number 13 would be choice B. Now, it didn't say that we're necessarily using all of these, but I'm going to assume that's true unless we get to a problem where it doesn't make sense to use one of the remaining ones that I have here. I put multiplication property. I hope you're paying attention to this, because that's the wrong one. I added the same thing to both sides. That's the addition property. My bad on that. Okay, so good to double check your work, to think about what you just did. I do that sometimes. Yep, I make mistakes sometimes, but I try to fix them as best as I can. Number 14, if UV equals VW, then VW equals UV. What would that be? It looks like you're switching the two things around, but they're still the same statement, just with the things flip-flopped. That is the symmetric property of equality right there. So that would be choice A. So we've used A, we've used C so far. B and D seem to be left. Let's see if this is a matching problem, or a set of matching problems where you use each one exactly once. So if AE equals EG and EG equals JK, then AE equals JK. This is very much like the law of syllogism. You have that first thing here equal to a second thing here, the second thing equal to a third thing, therefore the first thing is equal to the third thing. That right there is the transitive property of equality. That's that one in action. So we've got choice D for number 15. Let's see if it makes sense to say that 16 is the multiplication property of equality. So here you start with the measure of angle K equals 9 degrees, pretty small angle there. But then they're saying if you multiply that side by 3, take 3 times the measure of angle K, and take 3 times 9, do you get this statement? 3 times the measure of angle K equals 27? Sure do. 3 times 9 is 27. So choice B makes perfect sense for number 16. So we've used each choice exactly once Let's move on. All right, so stating a reason for each step with each one of these. 17, 18, and 19. Let's see. I feel like I might need some more space. I think I can squeeze it in though. Here, let's give it a shot and see what we got. That rhymed. I wasn't even trying. Does anybody have a peanut? No. Stop rhyming, I mean it. Does anybody have a peanut? Do you know the movie? If you do, comment section. Feel free. Tell me what movie that was. All right, 17. It was a poorly quoted job, poor quoting job by myself, but it's a classic movie. 5 times 3y plus 2 equals 25. We're starting off with that. So this is given to me. I'm going to write that in there as a given, stating a reason for each step. So from here, I can distribute the 5 to both parts there. That would be 15y plus 10 equals 25. So I just said the magic word there, distribute. So this is the distributive property. You could say the distributive property of equality if you wanted to. I'd accept either one. Check with your teacher and make sure they're okay with either. You might want to write out the whole thing depending on your teacher. So if I subtract 10 from both sides, again I said the magic words there, subtract instead of distribute up here. Now I'm subtracting. I'm going to be left with 15y equals 15. So what property was that? That was the subtraction property. I usually write out the whole word subtraction because otherwise it looks like substitution possibly. So subtraction property of equality, both of those would work. And then finally I'm dividing both sides by 15 to get y by itself. That leaves me with y equals 15 divided by 15 is 1. So I solve the equation. The reason for my last step there would be the division property or division property of equality. Very nice. Number 18. So here we have what's given again, 8t minus 4 equals 5t plus 8. So I'll keep doing my reasons here in green. Okay, I'll do one step at a time. I'm trying to get t by itself on one side of the equation. So I could have subtracted 8t from both sides, but I'm a positive guy. I like to keep things positive. I'm going to subtract 5t from both sides instead. That'll get that to cancel out right here, just as the 10's canceled out here and the 15's here. You don't have to show the cancellation, but if that helps you, go ahead and do that. You're left with 3t minus 4 equals 8. So to me, I just subtracted that. That's pretty clearly then the subtraction property or subtraction property of equality. And then if I add the same thing to both sides, it's going to get the 3t part by itself if I add 4 to both sides. I'm left with 3t equals 12. I just added the same thing to both sides. That sounds like the addition property to me. So addition property or addition property of equality. And then finally, dividing by 3, dividing both sides by 3. That canceled there. The 3's are going to cancel if I do that. And I'm left with t equals 4. What property was that to finalize the solution? Divided division property. Divided both sides by 3. Number 19 looks like a pretty similar problem to these ones. You just have, it's an interesting problem. How do they expect us, or what do they want us to solve here? I'm not exactly sure. They've got a D and a C. We can't really solve this one. Give me a minute. I'm going to see what the book says about this one. We can't really solve for a variable unless we leave it in terms of the other variable. But alas, I spoke too soon because I didn't notice something here. I was looking at it too quick and You'll see what I mean in a second. So just go with it for now. We do want to put our first step here as given. Just needed to look a little closer at the problem there to see what would happen here in this first step. So I noticed that I have a negative 2c on both sides. If I added 2c to both sides, the c's are going to go bye-bye. They're going to drop out completely. So 2c added to both sides. I just did the addition property right there because I added the same thing to both sides. I'm left with 23 equals plus 11d equals 12. So that was the addition property. From there, now I can just solve for d. I'm not going to be left with two variables. The c's have gone away. They're no longer with us. If I subtract 23 from both sides, I'm left with, this canceled, I'm left with 11d equals, this would be negative 11. So that right there, subtraction, same thing from both sides, subtraction property. And then same final step as the previous two problems, divide both sides by what's in front of the variable, get the variable by itself. In that way you're going to be left with d equals negative 1. And so what was the final step there? That was the division property. And so I think we just have a couple left here. We're going to write a 2-column proof for number 20. All right, let's get out my straight line tools here. Okay, I'm good to go. I've got my statements on the left and my reasons on the right. So always start off with what? Always start off with what you are given. So we're given these two statements. Segment AE is congruent to segment BD. And we're also told that CD is congruent to CE. Step 1, that's given. Step 2, well, AE, let's draw these things on the picture as well. Always, always, always draw things on the picture as you go, as you prove things. That will allow you to prove other things. So AE is congruent to BD. This is a little hard to draw there on the picture because AE kind of crosses through C. So I'm just going to keep that one in mind. But I'm also going to remember that CD, I also know that CD is congruent to CE. So these small ones are congruent to each other. And the big one here is congruent to the big one here. Okay, I'm trying to prove, what am I trying to get to? My final step is that AC is congruent to BC. So I need to end with that down here. AC is congruent to BC. So this smaller part is congruent to this smaller part. Well, if I have the whole segment and I subtract this part, and I have the whole segment here and I subtract this part, remember AE is congruent to BD. So something that's congruent minus something that's congruent is going to equal something that's congruent minus something that's congruent, like that. So really we're using the addition property of equality, of segment addition. So we're going to use a segment addition property here. A better way to say that, the segment addition postulate, if you consider the way our book talks about it. So the segment addition postulate tells me that this is true, or both of these statements are true. That AC plus CE is equal to AE. And it also tells me that BC plus CD equals BD. The smaller parts of the segment make up the whole segment. So that's a segment addition postulate. So segment addition postulate tells us this. We can say that AE equals BD, and we can also say that CD equals CE by the definition of congruence. If something's congruent, that means they're equivalent to each other in measurement. So I'm just going to use that. Depending on how picky your teacher is, you may or may not have to go from that to that. I would like you to do that, though. If you're one of my students, I think this is a valuable thing to say. If you're given congruent and you're using equations, we don't really use congruent parts in equations, or we're technically not allowed to, so we want to switch that around a little bit first here. So we've got AE equal to BD. I'm going to circle some things up here. AE equal to BD. So this equals this, or underline circle things. And I know that CD equals CE. This one equals this one. So how can I get to AC being equal to BC? So in a proof format, we have to be very technical, precise with the way we're putting things in order here. Since I know that these two things are equal, right here and right here, AE and BD, I'm told that they are congruent. I can set congruent things that I know are equal to each other, things that I know that they equal as well. Since this equals AE and this equals BD, I can say that this one, AC plus CE, equals BC plus CD. So that statement, AC plus CE, must be equal to, this equation must be equal to BC plus CD. This expression, I mean, not equation. This expression must equal this expression if these two are in fact congruent to each other. And now we know, first of all, that this would be, I'm basically using the substitution property. I'm taking AE what it equals, I'm substituting that in its place. I'm taking BD what it equals and substituting that in its place. And I'm saying I know these two are equal to each other based on what I'm told up here and what I've proved down here, so I can say that these things are equal to each other by substitution. And so step 5, we are subtracting equal things now from both sides. I can subtract CE and CD from both sides. I can just say, hey, these go away. They're equal to each other. If I subtract equal things off of both sides, what am I left with? I'm left with AC equals BC. And that would be by the subtraction property. So I subtracted two things that were equal to each other from both sides of the equation. You could say a subtraction property of equality would be good as well. And so finally, AC then would be congruent to BC based on the definition of congruence or congruent segments. We should probably write that in there. So definition of congruent segments, because you can have other congruent things too. So definition of congruent segments, if they are equal to each other in measure, then they're also congruent to each other. All right, and then finally number 21, another 2-column proof. So here's my 2 columns. Oh, that looks so pretty. Statements and reasons. Okay. Let's see what we got here. We have a few things given to us. Let's start by writing those things down. Angle 1 and angle 2 are complementary. We have angle 3 and angle 4 are complementary. And then finally, angle 1 is congruent to angle 3. So all of these things we can just assume are true. They are given to us. So let's, in the picture, designate or denote some things there. We've got angle 1 and angle 3 being congruent, so I'm going to put an arc mark there and there. I know that 1 and 2 are complementary, so 1 and 2 add to 90. So this one and this one add to 90 degrees, and I know 3 and 4 are also complementary. These also add to 90 degrees. So in all, I've got 180 degrees there. This has to be a straight line then. Alright, let's see what I'm trying to prove here. I'm trying to prove that 2 is congruent to 4. If I knew 1 and 3 are congruent, I already said that 1 was congruent to 3. And if I know that these two add to 90, and I know that these two add to 90, it seems pretty logical then that if I take 90 and subtract something here, and 90 and subtract something that's congruent over here, what's left over would have to be congruent as well. So you could go and set up equations, say things like the measure of angle 1 plus the measure of angle 2 equals 90. You could say the measure of angle 3 plus the measure of angle 4 equals 90. And you could subtract congruent things from each other and be left with angle 2 is equal to the measure of angle 2 is equal to the measure of angle 4, therefore angle 2 is congruent to angle 4 in a very similar way to what we did here with segments. However, I'm going to make our lives a little easier on us on this one because there's actually a theorem that's already been proven in our book that we can use to say just that. So we can go right to the end here. This is very rare that this happens, but we can say that angle 2 is congruent to angle 4 by there was something called the congruent complements theorem. I'd like to bring that up in the book just a second here. And I lied. I am actually going to leave that to you if you want to look it up in the book. Congruent complements theorem. It describes in a proof format what I verbally explained to you. So if you had here two things that add to 90, two things that add to 90 here as well, you subtract congruent things from 90 and 90, you're left with things that also have to be congruent here with 2 and 4. Okay, I think that does it. That's it. Hopefully you used this video in the way that I suggested and recommended. You didn't just go to the video and copy everything down, because that's really not going to help you in the long run compared to your test that you're trying to prepare for. If you're getting points for doing this review, those points are probably very, very little in comparison to the amount of points you're getting on the test. So please be ready for any test or quiz you might be taking to demonstrate your knowledge, to demonstrate your understanding of the material at hand here in Chapter 2. Good luck. Do your best. Study hard. Go get 'em.